Moment of inertia is the resistance of an object to accelerate, or how hard it is to change an object's rotation rate. And I kind of threw it out at you saying, all right, it's proportional to mass times radius squared, but where did this proof come from? Let's take a look at it more closely. If I'm trying to rotationally accelerate something, I need to put a torque on it, and I gave you torque is equal to I times alpha. I put a torque on it, it's going to accelerate. I also say that the rotational kinetic energy is 1/2 I omega squared, just like 1/2 mv squared. Where if something is rotating around, I know there's kinetic energy because a mass is moving with some velocity v. So I gave you these two formulas, but all I really know is F equals ma, and the kinetic energy is 1/2 mv squared. Let's take a look at these and see why this formula fits and why the moment of inertia is mr squared. We just start with kinetic energy is 1/2 mv squared, but if we're rotating in this direction at some radius r, we know the speed is omega times r. This is just a simple substitution, and I can square the r and bring it over here, and I have 1/2 mr squared and omega squared. The reason I like this is because this describes the object itself. If this is a rigid body, a bar with a mass at the end, this is about the bar, this is about its motion. And so this form is very nice, just like 1/2 mv squared, but instead of just mass, we have the moment of inertia, which is mr squared for this mass out here at this radius. Similarly, if I'm applying a torque here to try to angularly accelerate this bar that's pivoting about this point, all I really know is the force is equal to mass times acceleration. So I apply some random force at some angle, and then I realize, well wait, if I separate this up, the parallel component of the force just pushes against the compression of the bar. The only thing that accelerates the mass is this perpendicular component. And so I can say the perpendicular component of the force is equal to the mass times acceleration in this direction of that mass. But I also remember the acceleration in the perpendicular or tangential direction is equal to the radius times rotational acceleration, alpha. And so I put this in terms of rotational motion. But this is not in terms of rotational motion. What if I'm putting a torque on this in order to get that force? I'm pushing it like this, or there's a screw here, or there's a motor trying to turn it. Then I have to say, well, wait, a torque would be equal to that perpendicular force times the radius, or the perpendicular force is equal to the torque divided by r. So I put that in, torque divided by r is equal to this perpendicular force, which is equal to this. So if I set the first term equal to the last term, I have torque over r equals mr alpha. And I multiply through by r, and I've got this. And so again, we have this term here that only depends on the object itself, the bar and the mass, and this is about the motion of the system. And so again, this is a nice form. Torque is equal to I alpha, just like force is equal to ma. And we see that I, the moment of inertia, is equal to mr squared. So the moment of inertia of a particle is equal to mr squared, where r is the distance from the center of rotation. But what if we have many particles and they all are rotating as a solid body? So this is a chunk that's moving like this, and now we have VA in that direction, but there's going to be VB in this direction. So my intention is to show you how, given any body like this, and we're going to move on to bodies of infinite particle number, we just have to take the sum of all the mass times radius squared of all the particles. Let's just start with 2. We remember that the kinetic energy is equal to 1/2 mv squared, and I can make the substitution of omega r, and I get I omega squared, where I is mr squared of A. But now we have to correct this and say this is omega A times r of A. And this is going to be equal to omega B times r of B. And so when we substitute this in, I get 1/2 mv squared of A, which is Ra omega A squared plus 1/2 the mass of B times RB omega B squared. Now what I like about this is that while they don't have the same radius and they don't have the same mass, they have the same omega. When this guy goes around once, this guy is going to go around once. The rotation rate is the same. So I can pull that out and I end up with 1/2 MA R squared A plus MB R squared B times omega squared. And so what we have here is just the sum of the squares of the radii times their masses, or the sum of mr squared. Likewise, we can make the same argument here. The torque is going to be equal to the torque to rotationally accelerate mass A plus the torque to rotationally accelerate mass B. And you're going to end up with mass A times r squared A times alpha A, the torque necessary to accelerate this guy, plus the torque necessary to accelerate B in this direction. But because it's a solid body, their rotational acceleration is the same. And I can pull that out. I end up with the sum over A and B of mass times radius squared times alpha of the system. Again, we see how we can take a bunch of masses that are rigid, model it as a solid body, and the torque necessary to accelerate it rotationally is just I times alpha, where I now is not just mr squared, it's the sum of all the mr squareds of all the masses. In section 10.3 of your text, they give you all the formulas for all the different moments of inertia for different object shapes. And all we know is that if you have a point mass, the moment of inertia is mr squared, where r is the distance to the center of rotation. And if there's many points of mass, you just add them all up. So I want to find out why is it that if I have a ring, its moment of inertia is mr squared, but if I have a disk, its moment of inertia is only 1/2 mr squared. And conceptually, we should be able to see that because if you have a disk, some of the mass is at a smaller radius. And so it's going to be easier to turn, or it's going to have less energy than if all the mass were out at the full radius. But where does the 1/2 come from? And how can we find these moments of inertia for an arbitrary shape? So the first step is to understand why the moment of inertia of a ring is the same as for a point mass. So let's say I had just a ring of radius r. Why would its moment of inertia be just as if it were a point mass? And so I say, okay, let's just add them all up. Mr squared of each little tiny mass here. It turns into an integral and we integrate over all the little bits of mass. But they all have the same radius, so we can pull the radius out, so the integral collapses to mass. And so we can see, yeah, a ring has a moment of inertia of mr squared because all the mass is at the radius of the ring itself. It's all at the same radius. So when we have the mass distributed out at different radii for a disk, then we can't do this. This won't collapse. So we have to go in and look at all the different radii. And so I set this up. Let's take a disk of mass m. The mass is equal to the density times the volume of the disk. And the volume is the area, or 2 pi r, times the thickness. So now I can solve for the density. The density is just equal to the mass divided by the area times the thickness. And what I'm going to do is I'm going to say, okay, this is pi radius squared, where capital R is the full radius of the disk. And I'm going to assign thickness is equal to 1 because it's all the same, so I can just drop all this crap out and I don't have this here anymore, and I can look at this as just a surface. So now, if I want to look at a little chunk of mass, for instance, on the disk, I can say the little bit of mass is just equal to rho times the little bit of area. So the plan is to go back to here and to integrate over all the little bit of dm times r squared, and we're going to integrate it over the whole mass, but that's going to change to integrate it over the whole area because I've transferred my little bit of mass to a little bit of area. So what's a convenient area to use? Well, I'm going to use an area that is a ring because I know that I can get the whole ring and it all has the same radius. So I'm going to write this as equal to rho times 2 pi r dr. Okay, because the area of this ring is the length times the thickness. The thickness is dr, the little infinitesimal radius, and the length is 2 pi r, is the circumference of the ring. Now I can substitute this all in. dm is just rho times the length times the thickness times r squared. And now I have to integrate this all the way over the whole disk, but that's just going to be from 0 to capital R. We pull out all the constants, rho and 2 pi, and we have r cubed dr from 0 to r. Well, that's just r to the 4th divided by 4, or pi rho over 2 r to the 4th. But what's rho? We already have rho is equal to the mass divided by pi r squared. The pi's cancel, the radius squares cancels with 2 of the radii in the numerator here, and we end up with mr squared divided by 2. And so by doing that integral, I was able to get this 2 in the denominator, and the moment of inertia of a disk is 1/2 mr squared, or the moment of a rod spinning in this direction is 1/2 mr squared. Because even if it's a rod, if it's very long, everything rotating has the same radius regardless of where it is along the rod. It's just how far it is from the center of rotation.